Hi, it's Mr. Anderson, and this is AP Physics Essentials, video 44. It's on simple harmonic motion. Imagine we take an object that's in equilibrium and we push on it. But it doesn't just move away. There's a restoring force that returns it towards equilibrium, and another returning force that returns it towards equilibrium. And so what we get is this simple harmonic motion. What would be an example of this? Pushing a child on a swing. And so there are really two examples we'll do in AP Physics. One is a mass spring oscillator, and so it's going to bounce up and down like this, or a pendulum that's going to swing back and forth like this. So equilibrium is going to be right in the middle, but these restoring forces continue to bring it back towards equilibrium. And so if you have an object moving towards equilibrium based on restoring forces, we call that simple harmonic motion. And so here are the two types we'll talk about in AP Physics. Now, an important characteristic with each of these is the period of that harmonic motion. Period is always going to be measured in seconds, and it's time. So it's the time it takes on this oscillating spring to move from here to bounce up and then to bounce back again. Or for a pendulum to swing from here over to here and then back again. And so in a mass spring oscillator, how do we increase the period? Well, the easiest way to do that is simply increase the mass. As we increase the mass hanging from the spring, the period is going to get longer. How do we decrease it? Well, we can change the stiffness of the spring. As we make it stiffer, then we're going to make that period go down. What about a pendulum? How do we increase the period of a pendulum? Well, we do that by just simply changing the length of the pendulum. Now, what's interesting about pendulums is the mass doesn't have anything to do with it. And so how do we then decrease the period of the pendulum? Well, we have to change the gravitational field strength. As we increase that field strength, then we're going to decrease the period. And so with both of these forms of simple harmonic motion, you should be able to identify the position of the object at any time, its relative velocity and acceleration, and figure out when these are at a maximum and when they're at a minimum. And so let's look at some simple harmonic motion. This one we've got it horizontal with two springs, and so we can see its motion. Equilibrium is going to be right in the middle. And so as I pull it towards this side, there's going to be tension in this spring right here, and it's going to pull it towards the right. And so that restoring force is going to move it towards equilibrium. Now it's going to move in that direction. Now this other spring is going to move it back towards equilibrium like that. And so what we're going to get is this simple harmonic motion. What's cool about this one is there's an accelerometer with little LEDs so you can see the acceleration of the object. You can see right in the middle there's no acceleration right in the middle. And so what do you have to do in videos like this or in problems like this? You have to be able to identify the position of the object and the velocity and acceleration. When are they at a maximum? When are they going to be at a minimum? And so let's use this scenario. And so I'm going to pull that object towards the left. And so now I've let it go. And so at this point right here, as it's starting to move, where's our position going to be? It's going to be maximum towards the left. What about our velocity at this point? It's going to be minimum. It's going to be 0. And what's going to be our acceleration? Our acceleration is going to be maximum towards the right. We're going to have great acceleration at this point. Let's let it go for a second, and I've paused it again here right in the middle. What's our position? Again, it's minimum. It's at 0. What's our velocity? Well, it's accelerated, and now our velocity is at a maximum at this point. What's our acceleration? There's no acceleration right when it's in the middle. Let's let it go again. It's going to move over to this side. Now our position is maximum to the right. What about velocity? It's back to 0 again. Where's our acceleration? It's going to be maximum now towards the left. And so let's do some little experimentation with a mass spring oscillator. We're using a PHET simulation, and let's look at how the mass and that stiffness of the spring affect the period. And so I'm going to take a weight, put it on here, and then we'll measure the period just qualitatively. So that's going to be the period. So that's a 50-gram mass. Now let's put a 100-gram mass on there, and let's listen to the period again. Okay, so you can see that we're slowing down the period as we increase the mass. Let's put 250 grams on there. So you can see that as we increase the mass on that spring, then we're increasing the period. But now let's play around with the stiffness of the spring. We call that the spring constant. So now I've made it a stiffer spring. I put that 250-gram mass on it, and you can see the period is now decreasing. And so by increasing the stiffness of the spring, we are increasing decreasing the period rather of the spring. Now let's really make it a soft spring. What happens? You can see the period gets really, really large. And so in summary, what have we learned just from this experimentation? That if you increase mass, you're going to make a longer period for that harmonic motion. And if we increase the stiffness, then we're going to make it a shorter period. If we look at that quantitatively, so if we look at the actual period of a spring like this, what's really affecting it are two things, the mass and the spring constant. And so you can imagine just looking at this algebraically, if we increase mass, what's going to happen to the period? The period is going to increase because it's in the numerator. What's going to happen if we increase the constant of the spring, or the spring constant, as we make it stiffer, as this number gets larger in the denominator, then we see that the period is going to become less. Now let's look at a pendulum. Again, another PHET simulation. So I'm going to move this to the side. I'm going to try to drop it at about a 30-degree angle. And this one has a little photo gate timer, so I can time how long it takes back, or how long it takes to get back to that original position. So we can see here that we've got a period of 2.862. Now I'm going to make the pendulum have a smaller length, dropping it from the same angle, and you can see that the period now is less. It's 2.415. Now let me make it even less. I'm going to try to drop that weight again at a 30-degree angle. Set my photo gate timer, and you can see that the period is becoming less. So as we decrease the length, what are we doing to it? We're speeding it up, or the period is decreasing. Now watch what happens as I change the mass now. As I change the mass, drop it from a 30-degree angle, start my photo gate timer, you can see that it doesn't affect it. So mass doesn't affect the period. But what does, remember, is going to be the gravitational field strengths. So now let me change it to the moon, and you can see that the period is increasing. It's slowing down. Let me change it to Earth. Now it's speeding up. What happens if we make it Jupiter? It's really speeding up. Or if we make it nothing, it just continues moving like that. So if we look at that quantitatively, or rather qualitatively, as we increase the length, we got a longer period. And as we increase the gravitational field strength, then we got a shorter period. If we look at that algebraically, this is the equation. Length is going to be on the top, you remember. And so as we increase the length, we're going to increase the period of the pendulum. What happens as we increase gravitational field strength? As we increase that, then we're going to decrease the overall period of the pendulum. Okay, did you learn to predict which properties affect harmonic motion? Again, it's a restoring force moving it back towards equilibrium. Could you design and plan and collect data to ascertain what characteristics are affecting the period? Again, in a spring, it's going to be the mass and the stiffness of the spring. If we're looking at a pendulum, it's going to be the length and the gravitational field strength. And finally, could you figure that out quantitatively? What happens as we increase length, for example, to our period, or gravitational field strength? Well, I hope so, and I hope that was helpful.